Part of the goal of low impact development is to reduce stormwater and manage stormwater, but part of stormwater management also involves erosion control. Erosion can be caused by wind, called aeolian erosion, which occurs when high winds remove soils, particularly when soils are dry and there's no vegetative cover. Wind erosion can temporarily halt construction practices if topsoil isn't covered well and can lead to more expensive replacement of that topsoil. Development can also exacerbate wind erosion permanently by changing the topography of the land by removing natural windbreaks such as dense vegetation, trees, and other soil cover. Most commonly, however, we deal with water erosion or fluvial erosion, caused when runoff carries away particles, and it usually occurs in sheet erosion, rill erosion, gully erosion, or stream banks erosion and collapse. Fluvial erosion of all types is caused by increased runoff, particularly from development. This is a relatively old image, but it still illustrates well the different types of erosion. Sheet flow, formation of the sheet flow into very small channels called rills, and those rills, if left unattended, will eventually form gullies that may erode infrastructure. Development most commonly contributes to eroded soils because of the disturbances to the natural hydrologic conditions of the location, including the loss of natural vegetative land cover. Low-impact development best management practices for stormwater management go far in conserving soil loss by preventing water erosion. With respect to wind erosion, hedgerows, tree rows, and fence rows may be used as windbreaks to avoid conditions that create a permanent risk of soil erosion, particularly if these can be maintained in the construction process. A design with diverse plantings of trees of various heights and densities will not only buffer winds, but also provide habitat for native species. Erosion can be estimated through the universal soil loss equation. This includes the annual rate of soil loss due to erosion, which is a function of the rainfall factor, how much energy is emitted when a raindrop hits the surface, the types of soil or the soil erodibility factor, the length and grade of the slope, the type of soil cover, if it's bare dirt, if it's grass covered, brush covered, or wooded, and a support factor, P, but that's typically used for agricultural practices. For construction practices, it's usually assumed to be equal to 1. Typical values for the soil cover C are provided in Table 11.4. The remaining terms of the equation can be determined from site-specific soil maps, particularly from organizations like the U.S. Department of Agriculture and the U.S. Geologic Service, and other soil conservation agencies. We can see the impacts of erosion here and its impacts on infrastructure such as sewer systems and roadways. Environmentally sensitive design is especially concerned with steep slopes, one of several sensitive landscape features that in principle should either not be developed or else aggressively protected from erosion and instability. Steep slopes may be geologically stabilized through a variety of retaining wall systems. Soil erosion can be prevented with fabric-based methods that use plastic netting, wood mesh, nylon mesh, or paper twine to hold soil, seeds, and new vegetation in place for planting and cover. Steeper slopes may recover synthetic geotextiles and turf reinforcement materials, which will lock the soil in place but allow the water to permeate the soils. Geotextiles are synthetic materials purposely designed to protect soil and manage water flow in a variety of ways. They're easy to install, but can be unsightly and expensive to implement and repair. Some development may nonetheless generate permanent soil and sediment loss. Long-term controls may be required for these sites. Best management practices include settlement, infiltration, and wetland basins, and must be sized relative to the amount of estimated sediment from the universal soil loss equation. Permanent controls are designed to last 50 years or more and typically require little maintenance. In practice, they rarely achieve this longevity, may consume valuable land space, and also may be expensive to construct.